Chapter 10, Simple Harmonic Motion and Elasticity. First, the ideal spring and simple harmonic motion. We got an introduction to this in lab when we looked at Hooke's law, and that said that if you have a spring, which we could imagine our rubber band is a spring, then the amount that you have force that you have to put into moving it, to stretching it, is going to be proportional to the displacement. So the force applied is going to be equal to k, the spring constant, times the distance that you stretch it from its unstrained length, right? So that's shown here, where there's a sort of natural default unstrained length. You have to apply a force to stretch it any distance further. And with a spring, you'll also have to apply a force to compress it. And that's going to have to be in the same direction as you are trying to displace it, is the direction you have to apply the force. Remember, the spring constant K tells you about the stiffness of the spring. So if it's a really stiff or tight spring, then you have to apply more force to stretch it out, right? It's a bit harder to stretch it versus if it's a loose one. It's a low K value and it's really easy to apply a force to stretch it. And the spring constant units are newtons per meter. So newtons divided by meters, which you can see by dividing the force by x to solve for K. It's just newtons per meter. Now this is the amount of force that you have to apply in order to stretch or compress the spring. But oftentimes we want to focus more on the spring itself. So if we focus on the spring itself, then we have the restoring force of an ideal spring, which is another name for Hooke's law. So the restoring force of an ideal spring is exactly the same as the applied force, but with a negative sign. Why is that? Well, that's saying if I stretch my spring out in the positive x direction, it's going to feel a force in the negative x direction, trying to get it back to that unstrained length, right? So if I have a positive x, then I have a negative force. If I instead have a negative x, then I'm going to have a force in the positive direction, trying to get right back to where we were. So that's all that the negative sign is. It's to say that the force is in the opposite direction as the displacement. We once again have the same spring constant with units of newtons per meter. And so this is what we can imagine, the force that the spring feels given different positions, right? When it's in its unstrained length, then there's no force. But once you start stretching it, it feels a force trying to restore it back to that unstrained length. And so this is something we can actually observe. If you set up a spring with a mass on the end of it and it has this equilibrium position, the unstrained length of the spring is also referred to as equilibrium position. And we imagine that the surface is frictionless, so that the spring is free to stretch and compress either way. Then it turns out if you attached a pen to this and had it run in the background as a sheet rolled by, what you'd see is that the displacement of the pen, of the end of the mass here, from the equilibrium x equals 0 position would follow this sinusoidal path, right? So we could stretch the spring out to point A, and then if we released it, it would immediately start to move and it would reach its equilibrium place where it wants to be, but because it's moving, it's going to keep moving and overshoot that equilibrium until it reaches negative A. Equal distance, but on the opposite side of the equilibrium point, right? Either side of this, the amplitude is known as the distance from the equilibrium point to the furthest distance away from that. And it's always a positive quantity. So amplitude is just that positive distance, and then you put a minus sign if it is in the negative x direction. And this is a demonstration of simple harmonic motion. We see simple harmonic motion anytime we have a force that follows this form, negative kx, which is known as a restoring force, and we have a frictionless setup. Then that's our simple harmonic motion, which sometimes is abbreviated as SHM. that's certainly what we're focusing on this chapter. It's our big idea. This is the horizontal case. It turns out this also works in the vertical case. So if we instead start with our spring, it has some natural unstrained length, but then if we decide to hang some mass from the end of it, that's going to stretch it out a little bit, right? So I have some hand sanitizer here, weighed down with some batteries, but notice it stretched my spring or rubber band out to a greater length, right? That kind of settles in. This is now the equilibrium position of the spring and the mass. And that's what we used in lab, where we kept adding masses to find the new equilibrium position and how that distance shifted. But about this equilibrium position, we can still see simple harmonic motion, right? We could pull this down and then release it, and it would oscillate up and down across the equilibrium position, right? And that's what's trying to be shown here in the figure, is that from this equilibrium position, you could pull it down to the amplitude A, release it, and it would start moving. It would shoot past the equilibrium position until it compresses the spring at this higher point, and then it would again start to fall back down. And once again, the displacement as a function of time would follow this sinusoidal function, right? A nice smooth curve. We're going to take a closer look at how we can describe that sinusoidal function in the following sections. But for now, we just want to introduce the idea of simple harmonic motion, and that the spring will follow this equation of negative kx. It's a restoring force that opposes any displacements.